Welcome back to the Explainer. Today, we're cracking open the invisible architecture that is literally powering our modern digital world, web services. By the end of this Explainer, you're going to understand exactly how this wild, chaotic web of completely different technologies actually manages to communicate flawlessly behind the scenes. So let's get right to it.
Okay, let's dive into this. Imagine a super common scenario in modern software architecture. Say you've got this massive, robust enterprise app running on Java, but it needs to pull some very specific data from a totally separate Python-based microservice, maybe one that's crunching some intense machine learning algorithms. How on earth do they talk to each other? Well, in the real world, if two people don't speak the same language, right, communication just grinds to a halt, unless you have a translator. And programming languages? They're exactly the same. They are fundamentally different environments. A Java app natively has absolutely zero idea what to do with Python code. So how do we bridge this massive communication gap without, having to rip out and rewrite our entire software architecture from scratch? Which brings us to section 1, the universal translator. Enter web services. The answer to our massive communication problem is the concept of web services. Think of them as the ultimate diplomats of the digital realm. Their main job? Enabling seamless data exchange. Because of web services, you can actually have a huge monolithic system written in Java, interacting perfectly with a completely separate service written in Python, Node, Go. Honestly, it doesn't even matter. The underlying platforms, the technologies, the programming languages, they all become completely irrelevant. By operating on standard web protocols, these services make sure your systems don't need to share a native language or even run on the same operating system to communicate effectively. They just need to know how to interact with the service interface. It's brilliant. So let's look under the hood at the actual mechanics of this flow. It really all boils down to a classic client-server architecture that relies heavily on stateless communication. It goes like this. Step 1, the client, which could be your browser, a mobile app, or even another server, sends a request. Step 2, this request gets routed across the internet using universally agreed-upon protocols, usually HTTP. And then step 3, the server that's hosting the web service receives a request, crunches the business logic, packages up the right data, and then shoots a response right back down that same pathway. And what makes this whole setup so incredibly powerful is the stateless nature of it all. The server doesn't get bogged down trying to remember past requests from the client. Every single transaction is completely independent. That makes the entire system incredibly resilient and super easy to scale. Moving on to section 2, the modern standard, understanding RESTful APIs. The way we build web services has definitely evolved over the years, leading us straight to the modern standard that developers absolutely love today. If you're in modern web development, especially if you're a MERN or mean stack developer, REST is pretty much your daily bread and butter. Now, REST is an architectural style, okay? It's not a strict protocol. It's a highly refined set of guidelines for designing network applications. By identifying resources through standard endpoints, REST gives us a framework that is remarkably lightweight and just endlessly scalable. It literally forces you to think about your application in terms of resources, like users, posts, orders, rather than just abstract operations. And that is exactly why it's become the default backbone for modern web apps today.
Now, what's really interesting about this slide is how REST leverages data formatting to maximize efficiency. While REST can technically handle multiple formats, it almost exclusively relies on JSON. And JSON is incredible. It's extremely fast, highly human-readable, and it parses into native JavaScript objects instantly. This spares you the absolute headache of having to write complex, custom serialization and deserialization logic. Since most modern front-ends rely so heavily on JavaScript frameworks anyway, using JSON as your data format makes the communication between the client and the server lightning fast and exceptionally frictionless.
To actually manipulate this resource data, REST uses standard HTTP methods. I like to think of these as the action verbs of the internet. Let's look at the lifecycle of a user database, for example. First up, you use a GET request to fetch a specific user's profile. Simple enough. Next, say a new user signs up. You'd use a POST request to insert their brand new data into the database. Let's say a week later, that user decides to change their email address. You'd use a PUT request to update their existing record. And finally, if they decide to leave the platform entirely, you use a delete request to remove their data. And we really have to note the concept of idempotency here, especially when we're talking about put and delete. If you send the exact same delete request 10 times in a row, the end result is exactly the same as if you just sent it once. The resource is gone. This kind of predictable behavior is exactly what makes REST APIs so incredibly robust. All right, section 3, the structured veteran, understanding SOAP services. But REST definitely isn't the only way to build a web service. Long before REST took over the modern web, the enterprise world relied on a much more rigid, heavily structured alternative. Enter SOAP. Now, I want to draw a really sharp contrast here compared to what we just talked about. While REST is this flexible architectural style, SOAP is a strict protocol. It acts like the fortress of legacy systems. It operates with highly rigid rules for exchanging structured information. When you're implementing web services with SOAP, you don't get that loose, lightweight flexibility. No, you get a formalized set of instructions that both client and the server absolutely must follow to the letter.
Because of this strict nature, SOAP relies on some pretty heavy-duty technologies. First off, it relies entirely on XML for its data formatting. Now, XML has massive parsing overhead compared to JSON. It's highly verbose, wrapping literally every single piece of data in these thick, heavy tags. Secondly, SOAP uses WSDL to define the service interface. What this does is create a strict, uncompromising contract. Both the client and the server have to agree to this contract before any communication even happens. And let me tell you, anyone who's ever had to debug a 5,000-line WSDL file knows it practically requires a law degree to negotiate. If a single, tiny element in the message doesn't perfectly match the contract, the entire communication just fails. It is phenomenally secure and highly transactional, for sure, but it definitely comes at a pretty steep cost to bandwidth and processing power.
Which leads us to Section 4, the showdown, REST versus SOAP.
And this brilliantly illustrates the core differences between the two. On one side, we've got the lightweight, modern flexibility of REST, giving you that snappy JSON parsing and a highly flexible architecture that is just ideal for fast-moving mobile apps and public-facing APIs. Then, on the other side, we've got SOAP, which brings the heavy-duty security of XML and those strict, uncompromising contracts. SOAP is basically perfect for legacy enterprise environments. Think global banking applications or high-level telecom infrastructure, where a single miscommunicated byte could trigger an absolute disaster. It's really a matter of priorities. One prioritizes speed and scalability, while the other prioritizes ironclad structure and guaranteed delivery.
So, we've seen how web services, whether you're using the lightweight speed of REST or relying on the strict contracts of SOAP, act as the ultimate translators, totally erasing the barriers between fundamentally different technologies. They literally make the underlying infrastructure completely invisible to the endpoints. But it leaves us with a pretty fascinating question to think about. As our systems become completely agnostic to platform and programming language, what exactly are the next frontiers? What barriers are even left to break in global data exchange? Are we looking at achieving zero latency streaming? Is it real-time AI-driven data interpretation right at the edge? The digital world literally never stops evolving, and deeply understanding these foundational concepts is your absolute key to mastering whatever comes next. Keep exploring, keep building, and I'll see you in the next